Let's look at a couple of more examples, almost like case studies, but you know by now that these are not really typologies. These are kind of individual examples which may amount to some improved understanding of cyclogenesis. So this is Development of Mesascale Incipient Vortices from Mesascale Convective Systems, which we already mentioned in the context of easterly waves and so on. So this is an example of tropical cyclone Oliver that happened, I think, in 1993 off of Australia, and you can see here 4th February originated here deep in the tropics in the warm pool. In February the sun is to the south, so the warm pool is to the south, and then it evolved and went through various categories before reaching down here and disappearing. And it seemed to have evolved from a cluster of mesoscale convective systems. So you can see 4th February here at 6:40 a.m., 3:40, 23:40, and then 5th. So this is 4th, this is 5th, and basically there were a bunch of convective systems which merged and formed two larger scale mesoscale systems, and then it sheared off and formed one large mesoscale system with sufficient vorticity and reduced vertical shear and other favorable conditions to turn into a tropical cyclone, and then it got stronger and then weakened and died out. So as long as you have mesoscale convective systems and you have rotation, they are of course elevated. Convection is in the free troposphere and 500 millibar and so on, so you still have to reach to the surface to initiate the lower level circulation that the tropical cyclones have. And the other thing that happens with these rotations, in case it wasn't very clear when I talked about the Rossby radius of deformation, is that in the tropics the Rossby radius of deformation for given static stability and Coriolis and the equivalent depth, it's pretty big. And remember that when a perturbation has to survive, it has to be much larger than the Rossby radius of deformation. If it is smaller, it'll dissipate away. And cyclones, in that sense, if they have to survive as a perturbation in the background environment, then the Rossby radius of deformation has to decrease by the rotation. So that's what essentially happens when you have sufficiently strong vortex surviving from its incipient stage to the convection driving strong enough rotation with all the feedbacks that we talked about and picking up energy from the warm ocean. The other example is of the survival of a vortex. So this is Hurricane Danny, I think from July 1997, which formed here in the Gulf of Mexico, made landfall, crossed over, and then became stronger again over the ocean and transitioned into an extratropical cyclone. Apparently it started as a single vortex in a strongly sheared environment. So the question is, does a strong shear always tilt the vortex and dissipate it away, destroy it, or take away the energy from the convection and disallow the convection to grow tall and so on and so forth? But Danny started as a single cyclone and in a strongly sheared environment, or a reasonably sheared environment with not a very good structure, but the shear managed to tilt it and create a secondary vortex, as you can see, that managed to then pull energy from the environment and become a vortex that survived and grew into a cyclone. So here is the model simulations, idealized model and satellite imagery shown here, depicting the development of Hurricane Danny from weak tropical storm to marginal hurricane here. And the main idea here is that the vortex survival and evolution has to happen in whatever background environment there is, and the idea of surviving as a vortex and growing into a cyclone is again related to the ideas of Rossby radius of deformation and how the interaction of the this is called a pre-Danny vortex, and then it survived and became Hurricane Danny. How this survival and evolution happens with the scaling in terms of the perturbation and the Rossby radius of deformation that we talked about. Maybe I hadn't made that idea of the relation between cyclones as perturbations and Rossby radius of deformation clear enough when I introduced the idea a couple of podcasts ago. But just go back and look at it and see again that when the disturbance is much larger than Rossby radius of deformation, it can survive and the wind field adjusts to it. But main thing to remember is for the tropical cyclones is that in the tropics the Rossby radius of deformation is large because there is a 1 over f in the formula. So f is small in the tropics, hence the Rossby radius is large, which means the disturbance has to be larger, or the Rossby radius has to get large by rapidly ramping up the relative vorticity, which is acting through the change in the static stability and Bremsweiler frequency and so on. So essentially the vortex to survive and grow and feed on convection, its Rossby radius essentially ends up becoming smaller, so the environmental Rossby radius is reduced so that the vortex can survive and grow as a disturbance without the background velocity field dissipating it. Background velocity field will adjust to the cyclone if it survives, right? Various ways of saying it, but I hope the physics of it is understood. So we looked at all these tropical cyclogenesis ideas, and main thing you will still be left with is that there are some key necessary conditions, but they are never sufficient. So there is exact survival and growth into a cyclone or a hurricane depends on all these various factors that we talked at. So hopefully this understanding will keep growing and the forecasting of cyclogenesis will get extended in terms of the lead times, which will of course be part of improved hurricane forecasting as a whole.